Hello, and welcome to EEforEveryone, Part 8 of the Plant Life project. Today we're going to talk about the code for the control board that's in the Plant Life project. We're going to head over to the computer and look at some of the code, discussing why an object-oriented approach was used. Before we get ahead of ourselves, let's give credit where credit is due. I used a few libraries that really sped up my progress during this part of the project, and I recommend that you check out these libraries as well. First, I tried to use the Adafruit OLED library, but that didn't end up working out very well for me because I ran out of program memory due to the size of the frame buffer. Instead, I substituted the SS1306 ASCII library, which is a much leaner library. If your application doesn't require images or animations, this library works really well. Thanks, Greiman. Another library that I used is the DS1307 Rtc library, which allows for normal access to the real-time clock. It provides functions to read and write the current time, and it enables the battery backup by default. Awesome work, Paul. Thanks for sharing. There are a few critical parts of the code. First, the libraries that were mentioned before, which we are treating like a black box. As long as they keep working, we don't really need to dive into how they work. I've included the real-time clock library as a header and program file. This is because I intend to modify the library to provide access to the battery-backed memory space with a similar syntax to how one can write to the EEPROM on the Atmega 328P. Beyond these libraries, I've written some code that handles the inputs to the plant light, namely the enter button, keypad, and photocell. I've also written some code that handles driving the LEDs at a specific current, and turning on the fan when power sent to the LEDs will require active cooling. The remaining code handles the UI, setting menus, and pretty much everything else. Let's start on with the highest level, treating all of these classes as a black box. Oh, by the way, I used object-oriented programming to eliminate the need for copy-pasting code and making it more sustainable. There's some jargon associated with object-oriented programming, and I'm not super familiar with it, so it's possible that I will misspeak. For clarity, here's some of the object-oriented programming related jargon. A class is a collection of variables and functions that can be included as an object in a piece of code. For example, the SD1307 real-time clock library defines a class, and my use of it creates an object in my code. A method is a collection of instructions defined in the class. It behaves like a function, but you can set permissions to define who can call it. There's a lot to object-oriented programming, and this is really only scratching the surface. Once you start using inheritance and polymorphism, object-oriented programming really starts to flex its muscles. It is a powerful tool. Moving on, let's take a look at my top-level code. First, there's some pin definitions and instantiations of objects that need to persist throughout the execution of code. Those can be seen up at the top here. The serial port is opened and the display is initialized. Next, the real-time clock is initialized. With this complete, the button and UI objects are initialized, and then we enter the main loop of the code. Once we're in the main loop, we refresh the button with new analog values, refresh the UI with the current time, and allow the UI to set the time in the real-time clock when required. And that's it. Everything else is handled behind the curtain of the classes that we wrote. This top-level function serves to link the data from the different classes to one another as required. Please note that the UI is created with the display, button, and LED objects passed in with their pointers. It would also be possible to achieve the same function by inheriting the button, display, and LED classes as part of the UI class, which is something that I could do when cleaning up this code for release. Then again, I'm pretty sure that making software developers cringe is a core skill for hardware engineers, so maybe I'll just leave it the way it is. The button class is pretty straightforward, and there's a method written that creates an instance of the object, and that'll ask for the nominal ADC values for each button state, the tolerance around that value, and then there's the method to refresh the current state of the button. So there's a few methods that determine if there's a new key press to handle or read the current state out. Basically just return the value of the variable stored in memory. And if we dive into the actual code that I wrote, it's pretty straightforward. The only thing that was really interesting in this class, well, interesting to me, is the software debouncing. And really it just runs the algorithm for determining the button state. So it's just ADC value plus or minus the tolerance. And then as long as it gets 3 or 4 of those in a row, it will say, yes, this is indeed the button state. So that's how, when the voltage is, when the averaging capacitor or debouncing capacitor is discharging through the 1 megohm resistor, there'll be times when the ADC counts reading will actually be a valid state, but not for long enough for the software debouncing to think that it was actually a button press. Moving on to the LED class, this one's also pretty simple. The class takes in a desired set point for the 5 LED channels, which you give it by calling the red, blue, green, IR, or white functions. By calling those functions, you pass in the current set point in milliamps that you would desire. Behind the scenes, the helper method that converts the current to PWM set point value is called, and that will translate your requested current milliamps into the PWM value required to actually achieve it. So, pulling up the code, it appears as one might imagine. Here there are the 5 methods that can be called. It manages the sum of the total current flowing by first subtracting the old current set point and then adding the new current set point. Then calls the helper method that'll turn on the fan if the current is high enough, or turn it back off if the current has decreased below the threshold, which brings us to the UI class that is a total mess. See, I started getting close to having the plant light project code finished, and I was really excited to start testing it out. So I kept tacking on a little functionality here and there to this UI class until there are so many variables defined in the UI header file that you can't even see it on a 1440p monitor anymore. So it's not ideal. It does everything from turning the light on and off at the correct time of day, to taking in your user settings, to managing the EEPROM, handling day changes. The list goes on and on. We'll focus in on the methods that run the LEDs and show the current time, because those are the most general methods, and the rest of them are kind of a hodgepodge that makes it work. So when the refresh method is called, you pass in the current time that as read from the real-time clock. Normally, when refresh is called, we are at the root of the main menu, and we want to display the current status of the plant light. This status menu tracks the current time, quantity of sunlight expected for the day, current quantity of natural sunlight, as well as the performance for the last 5 days. All of these metrics are calculated in different methods of this class. This is done in case 0 of the switch statement that you see here. First, we call the show status function that displays that menu I just described, the run LEDs function that will turn the LEDs on and off when required, as well as fade in and out, and then an if statement that kicks the lamp into a settings menu. Let's take a look at that run LEDs function. This function calls another helper method that returns a Boolean 1 or 0, 1 if it's time to turn on the lamp, and 0 if it is not. This is the basis for turning the lamp on and off, as one might imagine. This masks the much messier and overcomplicated way that I store the user settings, so it's harder to forget what I did. This, along with a variable storing whether we were just on or off when the value changes, lets me know when it's time to fade in, fade out, stay on, or stay off. And that's exactly what this function does. It fades in, out, stays on, or stays off when it's the proper time to do so. One would notice that I am doing this fade by using delay statements instead of counting milliseconds, and that's honestly a bit lazy. If we were doing this fade properly, we would have counted milliseconds instead of using a delay that halts the entire processor for 200 milliseconds, But I didn't do that. Instead, I opted for the convenience and slight speed gain of holding the system for that 200 milliseconds while fading the LEDs in and out. I'll add that to my to-do list when I'm cleaning up this code. In reality, this delay doesn't really hurt the user experience much, since it only makes the user interface slightly less snappy for about 2 minutes out of a day, and besides, once the lamp is set up, there's no reason to interact with the user interface again. The lamp manages itself. That is the mess of code that I wrote. The reason why I like it is that because I wrote this mess of code as object-oriented code, when I need to change something, it's really easy. In my previous projects, simple modifications such as changing a constant in an equation could cause huge errors in the program because a function would be copied in multiple places and I would forget to change it in one place. Now, if I need to change the formula for converting from current to PWM counts, for example, all that we would need to do is open up the LED drive class. Once inside, if we modify the formula in the current to PWM helper method, changing this equation once will cascade throughout the program, updating every instance when we recompile. What I'm trying to say is that the code that I used to write was an unsustainable nightmare. And now that I'm using object-oriented programming, it's an unsustainable nightmare hidden behind pretty functions that I can reuse easily. There are many ways to organize code better than what I've done here, but these better methods help to facilitate collaboration. Unfortunately, I learned about transistors, radio frequencies, signals and systems, control systems, semiconductor. Point is, I never quite got around to learning how to make code sustainable and easy to collaborate with others. That isn't a part of my formal training, so I'm kind of shooting from the hip here. With the exception of the UI class, I think that I did a pretty good job of writing clean, sustainable code. Unfortunately, I haven't found a very elegant way to generate a large text-based settings menu. Perhaps I could have done something like creating a page object with defined hotkeys and text to display, and then make a higher level object that combined multiple page objects that are aligned into a virtualized 2D array like this. Then one could use the keypad to navigate from page to page. I don't know. I'm probably not going to do that because there's a lot of code here that would need to be reorganized, and it works the way it is. It isn't pretty, but it works until we touch it. I had fun sharing my software for the control board with you. While it's not the most organized software in the world, and it's still a work in progress, but it works pretty well. In fact, it works well enough for us to move forward and characterize the performance of the plant light. It will be especially helpful when tuning the current to PWM value equation. We will finalize this software in a future video, where I'll release it for your closer inspection. This will give some time for bugs to be exposed in the code as I gain more experience with the lamp and introduce a few key features that this lamp can benefit from, such as using the battery-backed SRAM as memory with more endurance than the EEPROM to recover from power outages more gracefully. We'll also add some monitoring of the speed of the fan so that we can know if the fan's actually spinning when we turn on the 12-volt rail, to help prevent thermal runaway in case the fan were to fail. If you think this video is great, let me know by hitting the like button, subscribing to this channel, and leaving me a comment so I know what you liked about this video. I hope that you feel inspired to research object-oriented programming and learn how to create a class. A good place to start would be to write a class that provides a method for turning an LED on or off. A step up from there, as far as complexity goes, would be to create a class that controls a 7-segment display, handling the multiplexing for you. Pass in a number, and it handles the rest. Most of all, I hope that you learned something great today, and I hope to see you again soon. Bye!